For more than a century, one cosmic monster has puzzled astronomers. OJ-287, a pair of supermassive black holes locked in a violent dance. Their collision shakes space itself, sending ripples across the universe. Today we explore what makes this system so extraordinary. If you enjoy discoveries like this, please like, subscribe and share, and tell us in the comments, what would you ask about a binary black hole this powerful? Thank you for watching. Now let's begin. On the largest scales, the universe around OJ-287 appears as a vast, almost delicate web of matter and light, stretching across distances of billions of light years and linking together galaxies, groups and clusters into an intricate structure shaped by gravity over cosmic time. Thin threads of dark matter, which is a form of matter that does not emit or absorb light but does contribute mass and gravity, guide ordinary gas into long filaments. And along these filaments, galaxies condense and gather in knots, where the density is slightly higher. Between the filaments lie wide low-density regions called cosmic voids, where relatively few galaxies are found, and where the space between them is more nearly empty. The pattern is not random, but reflects tiny variations in density that were present in the early universe and slowly amplified by gravity over billions of years, so that what begins as slight ripples in a nearly uniform medium grows into a pronounced network of structures on scales that far exceed any single galaxy. In this setting, a bright active nucleus like OJ-287 is only one point of light among countless others, yet it can still stand out because of the extreme processes occurring in its core. The cosmic web itself can be traced in different ways. Large galaxy surveys map the positions and redshifts of millions of galaxies and reveal long chains and walls of galaxies hundreds of millions of light-years long. Clusters of galaxies mark the densest intersections of this web and contain hundreds or even thousands of galaxies bound together along with hot gas that shines in X-ray light and a deep shared halo of dark matter. Some of these clusters line up into even larger superclusters, forming a hierarchy of structure in which each level is built from the one below. Light from background galaxies sometimes passes close to massive concentrations of dark matter and is bent by their gravity, an effect called gravitational lensing which offers an independent way to map the invisible mass. Through these techniques, astronomers see the active galactic nuclei, the bright central regions powered by supermassive black holes, do not float alone in isolation, but are embedded in the same web of galaxies and clusters as more ordinary systems. OJ-287 belongs to this network and shares its large-scale cosmic environment with many other galaxies that also move within slowly evolving filaments and nodes. On these scales, the details of any one galaxy almost disappear, and what matters for the flow of gas and the assembly of structure is the overall pattern of overdense regions and underdense regions, sculpted by gravity and the expansion of space. Over cosmic time, gas streams along filaments into growing halos of dark matter, where it can cool and form stars and where central black holes can also grow. Galaxy interactions and mergers happen more often in dense environments where paths cross more frequently, and these processes may play a role in building up the mass of central black holes and in triggering phases of intense activity. Although the individual path that leads to a specific system like OJ-287 involves many details, its broad context is set by this cosmic web that directs material inward and shapes where galaxies and clusters form. The light that now reaches Earth from OJ-287 has travelled for billions of years, through expanding space, passing near other galaxies and groups, crossing voids and filaments, and carrying with it information about both the distant source and the medium it has traversed. The faint absorption and scattering it experiences along the way hint at the gas and dust between galaxies, while its redshift reflects the stretched wavelengths produced by cosmic expansion. In the background of this journey lies the almost uniform glow of the cosmic microwave background, which is the cooled remnant radiation from the early hot phase of the universe. And against this smooth backdrop, the clumped pattern of galaxies and active nuclei stands out as evidence of how gravity has transformed an initially simple state into a richly structured cosmos. Within this framework, OJ287 is one active point in a broad tapestry that includes quiet spiral galaxies, dense galaxy clusters, star-forming regions, and other bright active cores. It shares the same gravitational scaffolding and participates in the same slow evolution, even though its central engine happens to be unusually energetic and variable. Before moving inward to examine its host galaxy and core in more detail, it is important to recognize that at the largest scales, OJ287 is one small luminous node in a lattice that extends as far as observations can reach, a lattice shaped by dark matter. Ordinary matter and the expansion of the universe working together over almost the entire age of cosmic history. OJ287 appears to observers on Earth as a single sharp point of light projected against the faint glow of the constellation Cancer, a modest patch of the sky that holds far more than the unaided eye can see. Through a small telescope, it does not reveal spiral arms or a soft galactic halo, but instead looks star-like, which is why objects of this kind were first called quasi-stellar, meaning star-like in appearance but not in physical nature. Its light comes from a distance of several billion light-years so far that the light now arriving left the source when the universe was noticeably younger than it is today, and the expansion of space since then has stretched its wavelengths toward the red. This stretching is described by a quantity called redshift, which is measured by comparing the positions of known spectral lines, and in the case of OJ287, this redshift places it at a cosmological distance well outside the local collection of galaxies to which the Milky Way belongs. To visualize this distance, it helps to think of the Milky Way as one among many galaxies in a loose group called the local group, which spans a few million light-years, and then to imagine stepping out to larger scales, where that group becomes one small unit in a broader cluster and supercluster environment, while OJ287 lies far beyond in a region of space that light from our own galaxy reaches only after travelling for billions of years. On these scales, even a difference of 1 billion light-years corresponds to a very large change in look-back time, meaning the interval between when the light left the source and the present day, so that by observing distant active nuclei like OJ287, astronomers are also looking back into an earlier cosmic epoch. From our vantage point, this remote object occupies a tiny fraction of a degree on the sky, so small that a fingertip held at arm's length would cover not just OJ287, but a vast region of space around it, yet precise instruments can fix its position to a small fraction of an arcsecond, allowing observatory across the world and in orbit to return to the same target many times. Astronomers catalogue such objects using their measured coordinates in right ascension and declination, which are sky-based equivalents of longitude and latitude on Earth, and they assign names linked to survey programs and sky regions. The designation OJ287 arises from one such radio survey that mapped sources of radio emission and recorded their positions with sufficient accuracy to match them with optical counterparts. When radio telescopes scan the sky at long wavelengths, they find that some of the brightest compact radio sources coincide with point-like optical objects, and OJ287 belongs to this class. Its apparent brightness measured in different bands of the spectrum fluctuates over time, but even in relatively quiet phases it is bright enough in optical light that moderate-sized telescopes can monitor it, while in radio and X-ray bands it stands out as a strong emitter. In a simplified sense, apparent brightness tells how much energy from the source arrives at Earth per unit area, while intrinsic luminosity describes how much energy the source emits in total, spread over the entire sphere of directions. Because OJ287 is so distant, the fact that it appears as bright as it does implies an enormous intrinsic power output far greater than that of an entire ordinary galaxy filled with billions of stars. Determining this luminosity requires careful correction for distance redshift and the focusing effects of any jets or beaming, but even conservative estimates show that the central engine of OJ287 ranks among the most energetic known. The light that reaches Earth does not come from a single narrow range of wavelengths, but extends from radio waves through optical and ultraviolet light and into X-rays and sometimes even gamma rays, reflecting a combination of processes near the core. Observatories on the ground and in space contribute to building up this picture. Optical telescopes measure the visible light and track changes in brightness over days, months and years, watching as the source slowly brightens or fades or occasionally flares more suddenly. Radio arrays trace the longer wavelength emission that often originates in extended jets or compact cores. X-ray satellites watch for higher energy photons that reveal hot gas and extreme acceleration processes, and gamma-ray instruments, when they detect emission from this direction, add information about the most energetic particles involved. Together, these views define OJ287 as a bright, variable, compact source embedded in a distant galaxy, whose starlight is largely overshadowed by the glare of the central region. On the sky, it is one among many active cores, but its pattern of variation, its multi-wavelength output, and its location at a significant cosmological redshift make it a valuable laboratory for studying how supermassive black holes feed and how they release energy into their surroundings. Surveys that repeatedly scan the same region of the sky build up a record of its changing brightness, while pointed observations with larger telescopes fill in details of its spectrum, polarization and fine structure. Over more than a century of such efforts, OJ287 has shifted in status from a little-known radio and optical point source to one of the most closely monitored active nuclei in the sky. In simple observational terms, it is a point-like beacon in the direction of Cancer. Lying billions of light-years away, its light stretched by cosmic expansion and shaped by powerful processes near its center, and this small point on the sky, once plotted on charts and measured with ever greater precision, marks the location of an extreme system that links a distant active nucleus to the wider structure and evolution of the universe, the host galaxy of OJ287. Though long hidden beneath the glare of its active core, gradually comes into view as astronomers apply deeper imaging and more careful analysis, revealing that this bright star-like nucleus is anchored within a large, fairly massive galaxy, rather than floating alone in the dark. In ordinary images, the point-like central source overwhelms the surrounding light, so the galaxy does not show obvious spiral arms or a clearly defined bar, but when observers use large ground-based telescopes with good seeing or space-based instruments above the atmosphere and subtract the sharp central point spread function associated with the nucleus, a more extended halo of starlight appears around it. This diffuse glow is consistent with a galaxy that is either a luminous elliptical or a system that has been strongly shaped by past mergers, with stars distributed in a smooth rounded profile rather than in a thin rotating disk. The surface brightness of this halo, which describes how the light is spread over the sky, falls off gradually with radius, and its shape fits models that are commonly used to describe elliptical galaxies and the bulges of large disk galaxies. The colours of the extended light measured by comparing the brightness in different optical and near-infrared filters suggest that the stellar population is dominated by older redder stars with fewer young blue stars than would be typical of a strongly star-forming spiral. This pattern indicates that most of the stars formed long ago and have since aged and cooled with only modest ongoing star formation, although the intense radiation from the active nucleus can make it difficult to trace faint signatures of younger stars. In some deep images there are hints of asymmetries or faint structures around the main stellar body, such as low surface brightness features, and possible companions which may be remnants of earlier interactions or minor mergers. Galaxy mergers are common in the dense environments where massive systems grow, and when two galaxies combine their gas stars and dark matter halos interact often, leading to bursts of star formation and to the feeding of central black holes. Over time, repeated mergers can transform an initially disk-like system into a more spheroidal one, and the central regions can become dense and smooth, matching what is often observed in the hosts of powerful active galactic nuclei. For OJ287, the available data point to a host galaxy that is relatively massive and luminous, with a stellar mass that likely reaches hundreds of billions of times the mass of the Sun. Although the exact value remains uncertain because of the difficulty of separating host and nuclear light, and because different models of the stellar population can fit the data. The environment around the host galaxy also shows signs of being at least moderately rich, with several other galaxies visible in the same field that may form a loose group or part of a larger scale structure. In such settings, gravitational encounters between galaxies are more likely, and these encounters can funnel gas toward the central regions where it can feed the central black hole and trigger or sustain an active phase. Observations in the infrared where the effects of dust are reduced help to trace the underlying stellar structure more clearly, while optical imaging remains useful for mapping any dust lanes or patches inside the host. Some active galaxies show prominent dust features crossing their central regions, suggesting that cold gas has been brought into the inner parts, but in OJ287, the combination of bright nuclear light and limited resolution makes it challenging to identify detailed dust structures with confidence, and any such features remain topics of ongoing study rather than fully settled facts. Spectroscopic observations that attempt to measure the starlight from the host galaxy, rather than just the emission associated with the active nucleus, can in principle reveal the average ages and chemical compositions of the stars. For OJ287, such measurements are delicate because the nucleus contributes a strong variable continuum and in some states non-thermal emission that can mask the relatively weak absorption lines from the stars. Nonetheless, by targeting quieter periods, and by using sophisticated techniques to disentangle the different components, astronomers infer that the host contains a population of stars enriched in heavier elements, compared with the earliest generations, which is expected for a galaxy that has gone through many cycles of star formation and supernova explosions. The overall picture is that of a large evolved galaxy whose central regions host a very massive black hole system and an active nucleus that currently dominates the light output. The mass of the stellar component and the size of the galaxy fit within broader relationships observed between galaxies and their central black holes, such as the rough correlation between the mass of the black hole and the mass or velocity dispersion of the surrounding bulge. In the case of OJ287, the estimated mass of the primary black hole lies at the very high end of these relations, and uncertainties remain regarding how exactly the host galaxy and central mass co-evolved over time. It is possible that the system experienced particularly efficient episodes of accretion, or that repeated mergers built up the central mass faster than the surrounding stellar body, but disentangling these histories requires more detailed observations and modelling than are currently available. What is clear is that the host galaxy is not a small isolated system, but rather a significant stellar structure, embedded in a wider environment with a dense central region and an extended halo that gradually fades into the background of nearby galaxies and the cosmic web beyond. In deep, carefully processed images, the host stands as a faint, smooth glow around the intense point of the active nucleus, a reminder that even the most extreme central engines are anchored to galaxies built from ordinary stars, and that the large-scale processes of galaxy formation and evolution set the stage on which central black holes grow and become active. Within this galactic setting, OJ287 continues to shine as one of the brightest and most variable cores, its host barely visible, but fundamentally important as the structure that holds the mass gas and stars that have nourished its central engine over billions of years. In the late 19th century, long before digital detectors and automated sky surveys, astronomers at observatories in Europe and North America begin to capture the sky on glass photographic plates, patiently exposing wide fields for many minutes at a time, so that faint stars and nebulae can leave their mark as tiny dark spots in the emulsion. Night after clear night, these plates accumulate in wooden drawers and cabinets, each one a frozen record of the sky, at a particular moment, with coordinates carefully written in ink along the edges. Among the many points of light recorded on these plates lies the source now called OJ287. At that time, one anonymous speck in a crowded field in the constellation Cancer. The observers who take the exposures focus on cataloguing positions, magnitudes, and occasionally motions of stars, and almost no one looks for subtle changes in brightness from one plate to the next, because the task of comparing them by eye is slow and demanding. Yet the information is there preserved in silver grains that darken in proportion to the incoming light, and as decades pass, more and more plates accumulate from different telescopes and different observatories, creating a kind of time series archive, without anyone yet thinking of it in those terms. When the 20th century begins, photographic methods continue to improve, and the sensitivity and resolution of plates increase as emulsions are refined and telescopes grow larger. Survey projects are launched to map the sky more systematically, and some of these programs revisit the same regions many times, either to extend the depth of the survey or to check for new objects. Only much later do astronomers return to these collections with the new purpose to search for long-term variations in the brightness of objects that are now known to be active galactic nuclei. By then, radio astronomy has emerged as a powerful new window on the universe, revealing a population of strong compact radio sources scattered across the sky, some of which coincide with faint star-like optical objects. OJ287 enters the scientific literature as one of these radio sources identified in the 1960s as part of a survey and matched with an optical counterpart that appears point-like on photographs. Its coordinates and approximate brightness are measured and recorded, and it is noted as a variable object, but at first it is only one example among many. Over time, as more optical monitoring is carried out and more archival plates are examined, astronomers realize that the brightness of this source does not simply drift up and down in an irregular way, but shows episodes of strong brightening that may occur at roughly regular intervals measured in years. To test this impression, they gather plates from multiple observatories, sometimes travelling to archives to inspect them in person, and they carefully measure the photographic density at the position of OJ287 on each plate, converting that density into an estimate of brightness using comparison stars of known magnitude. The process is meticulous and slow, and each data point in the resulting light curve represents careful work at a desk or light table, but gradually a pattern emerges. The source appears faint or in a quiescent state for long stretches, then brightens dramatically sometimes by more than an order of magnitude in flux before fading again. These strong outbursts seem to come in pairs, with two peaks separated by a relatively short interval, and the pairs themselves recur on a timescale of about a dozen years. Because the plates span many decades, it becomes possible to trace this pattern back to the early 1900s, and even to the 1880s, extending the observational baseline far beyond what any single modern monitoring campaign could achieve. Each additional historical plate that contains a detectable image of the source adds one more point to the long-term record, and as the pattern of repeating double outbursts becomes clearer, OJ287 stands out among variable active nuclei as a system with an unusually regular long-term behavior. Alongside the optical work radio and later X-ray observations, provide further evidence that the source is highly active and variable across the spectrum, but it is this century-long optical light curve that offers the most striking clue that some underlying clock or orbital process may be at work. In the early stages, however, astronomers remain cautious because irregular sampling measurement uncertainties and the complex physics of accretion and jets can all produce fluctuations that might mimic periodicity. Detailed statistical studies are carried out to test whether the apparent regularity could arise by chance from a stochastic process, and while uncertainties remain, the accumulating evidence points toward a genuine long-term pattern. Through all of this, the physical nature of the central engine is still described in broad terms as a very massive black hole, accreting gas in the core of a distant galaxy, and producing non-thermal radiation, and sometimes jets that can vary on many timescales. The possibility that more than one black hole might be involved is mentioned as one of several options in early discussions, but it does not yet dominate the interpretation. At this historical stage, the key achievement is the recognition that careful work with old photographic plates combined with modern monitoring can uncover regularities in the behavior of distant active nuclei that would otherwise remain hidden. The drawers and cabinets of observatory plate archives, once seen mainly as historical records, turn out to contain precise timing information that allows the brightness history of OJ287 to be reconstructed over more than a century. And this reconstruction provides an essential foundation for understanding how this source has behaved over long periods of time anchored in real measured events, rather than in idealized light curves. By the time electronic detectors and automated telescopes take over much of the monitoring work, the role of the old plates has shifted from active data collection to archival support, but their importance for OJ287 remains clear because they carry the first clear clues that this distant star-like point is not just another variable nucleus, but one whose history of brightening and fading has been unfolding in a remarkably regular way since long before modern instruments turned toward it with focused attention. As observations accumulate across different parts of the spectrum, the point of light now called OJ287 begins to stand out not only as a variable object in old photographic plates, but also as a source with properties that mark it as an active galactic nucleus, a kind of central engine in a galaxy where a very massive black hole feeds on gas and releases large amounts of energy. In optical images, it still appears as a star-like point, but when astronomers split its light into a spectrum and measure how the brightness changes with wavelength, they find that much of its emission is not like the light from ordinary stars. instead of a spectrum shaped by many narrow absorption lines from stellar atmospheres. It shows a smooth, strong continuum produced by particles accelerated to high energies. In some states, emission lines from gas near the core are weak or nearly absent, a characteristic of a subtype of active nuclei, known for their nearly featureless optical spectra. Radio observations reveal that OJ287 emits strongly at long wavelengths as well, and the radio source is compact, indicating that the emission is coming from a very small region compared with the size of the host galaxy. When instruments sensitive to X-rays and higher energy photons point toward this source, they detect a hard variable component that cannot be explained by ordinary stellar processes. All of this points to a central engine where gas is being heated and accelerated under extreme conditions close to a very massive black hole. Another important clue comes from measurements of polarization, which describe how the electric field of the light waves is oriented. Light from thermal sources such as stars is usually only weakly polarized, but the emission from OJ287 often shows a high and variable degree of polarization, consistent with synchrotron radiation, from charged particles spiraling in magnetic fields at relativistic speeds. The level and orientation of the polarization change over time, indicating a dynamic magnetic environment, and further supporting the idea that the light is dominated by non-thermal processes in a compact jet or core. Combining these signatures, astronomers classify OJ287 as a blazar, which is a type of active galactic nucleus, where a narrow relativistic jet of particles and radiation is pointed nearly along the line from the galaxy to Earth. In this configuration, relativistic effects cause the emission to be strongly beamed, meaning that more light is directed into a narrow cone that happens to include the line of sight, and this beaming greatly increases the apparent brightness and enhances the observed variability. In simple terms, particles in the jet move at speeds close to the speed of light, and because of the way special relativity affects time and angles, radiation they emit is concentrated forward in the direction of motion. If that direction is nearly aligned with the observer, even modest changes in the jet can produce large swings in observed brightness. Time intervals measured by the observer are also compressed, so that variations that occur over a certain time in the rest frame of the jet appear faster when viewed from Earth. This helps explain why OJ287 can brighten or fade significantly over days or weeks, even though the physical size of the emitting region may be quite large. Detailed monitoring in optical and radio light shows that the flux can change by factors of several on relatively short timescales, and X-ray observations reveal episodes of heightened activity as well. In many blazars, the overall spectrum can be described in terms of two broad components, one at lower energies, attributed mainly to synchrotron radiation from the jet, and another at higher energies attributed to processes such as inverse Compton scattering, where the same high-energy electrons boost lower-energy photons to X-ray or gamma-ray energies. OJ287 fits broadly into this picture with a strong variable low-energy component and a higher energy tail that emerges during particularly active phases. The dominance of jet-related emission explains why the starlight from the host galaxy is so difficult to detect and why the central region appears so compact and bright. In the framework of active galactic nuclei, the central black hole sits at the heart of an accretion flow, a disk of gas that orbits and gradually spirals inward, heating up as it loses energy and feeds the black hole. Magnetic fields in and around this disk can twist and anchor jets that carry energy away along the rotation axis. In many systems, the jets are inclined at significant angles to the line of sight, so the emission is not strongly beamed and the active nucleus appears less extreme. In blazars like OJ287, however, the near alignment of the jet with the observer results in a dramatic amplification of the light, and in rapid, sometimes erratic variations that reflect changes in the flow of plasma and magnetic energy along the jet. Observational campaigns that coordinate multiple telescopes have shown that different wavelength bands sometimes brighten in step, while at other times one band lags or leads another, indicating that the regions producing radio-optical and X-ray light are related but not identical. For example, a disturbance moving outward in the jet, such as a shock wave or a knot of denser plasma, may first affect the inner higher energy emitting region, and later influence more extended parts that emit predominantly in radio wavelengths. These patterns provide indirect information about the structure and dynamics of the jet on scales far too small to be resolved directly. Despite the complexity, the broad conclusion is that OJ287 is not simply a quiet galaxy with a modestly active core, but rather a powerful blazar in which a relativistic jet dominates the observed emission and points almost directly toward Earth. This explains why it appears so bright even at a distance of several billion light-years, and why its light curve shows such pronounced and sometimes sudden changes. The identification of OJ287 as an active galactic nucleus, and more specifically as a blazar, provides a crucial framework for interpreting its behavior, because it links the observed properties to a physical model involving accretion onto a very massive black hole jet launching and relativistic beaming. Within this framework, the long-term pattern of outbursts revealed by historical plates and modern monitoring stands out as a notable feature that calls for a deeper explanation, but the foundation remains the same: a distant galaxy whose central region hosts a very massive black hole, a hot flow of infalling gas, and a jet that sends radiation and particles outward along a narrow, highly directed path that happens to intersect the vantage point from which the light is now recorded and studied. When astronomers place all available measurements of OJ287 side by side from the earliest photographic plates to modern digital monitoring, the brightness history of this distant nucleus unfolds as a long, uneven curve that stretches across more than a century, a record in which small, restless, flickering rides on top of larger, dramatic rises and falls. Each data point on this light curve represents a carefully measured brightness at a particular time, derived either from the density of silver grains on a glass plate, or from the counts recorded by an electronic detector. And when these points are plotted as magnitude or flux against date, the overall pattern becomes clear in a way that no single observation can reveal. On short timescales of days to weeks, the source shows irregular variation, brightening or fading by modest amounts, as conditions in the jet and accretion flow shift. This kind of short-term variability is common among blazars and active galactic nuclei, and in OJ287 it contributes a constant restless background to the light curve, like small waves on a larger swell. Superposed on this, however, lies a series of much stronger outbursts episodes in which the optical brightness increases by a large factor over weeks or months before gradually declining. These outbursts stand out in the historical record even when sampled sparsely by photographic plates, because the source changes from a relatively faint state to a clearly brighter one that is hard to miss when plates from different years are compared. As more data accumulate, it becomes apparent that these major events do not occur at random intervals. Instead, they cluster into pairs of outbursts that come relatively close together in time, followed by a longer quiet period before the next pair begins. The time between the first peaks of successive pairs is roughly a dozen years, measured from the late 19th century to the present, and within each pair the separation between the two peaks is shorter, often around 1 to 2 years, though the exact timing and shape vary. In many cases, the first outburst in a pair rises rapidly and reaches a sharp maximum before declining, while the second outburst is somewhat broader or more structured. But this is not a rigid rule, and each cycle has its own details. To quantify this behavior, astronomers compile all reliable measurements into a consistent scale, correcting for instrumental differences and calibrating the older plate-based magnitudes against modern standards. They then apply a range of statistical tools to test for periodicity, searching for dominant timescales in the data. Techniques such as periodograms and time series decomposition reveal a strong signal near the 12-year timescale, along with additional power at shorter times, associated with the spacing of the double peaks and with the underlying stochastic variability. Because the sampling is irregular and the amplitude of the outburst changes from cycle to cycle, the signal is not a simple sinusoid, and astronomers describe it as quasi-periodic, rather than perfectly periodic, meaning that a preferred timescale is present, but the exact timing and shape of events can drift. Even so, the repeated appearance of major double outbursts at approximate 12-year intervals over more than a century suggests that some robust, long-lived process governs the largest variations in the system. Modern monitoring campaigns using dedicated small and medium-sized telescopes distributed in longitude around the Earth fill in many of the gaps that older data leave. During anticipated active phases, observers organize intensive campaigns in which multiple observatories observe OJ-287 nightly or even several times per night, depending on weather and visibility, to track the detailed evolution of the light curve. These campaigns record not only the overall rise and fall of brightness during major outbursts, but also the finer structure such as small flares superposed on the main peak and changes in color or polarization that accompany the brightness changes. The result is that the most recent cycles are mapped in much greater detail than the early ones, and their profiles can be compared with one another, and with the smoother reconstructions of older events inferred from plate data. The long-term curve shows that some cycles produce stronger outbursts than others, with one pair perhaps reaching a higher peak brightness than the next, and that the relative strength of the first and second peaks can vary. This variability in amplitude indicates that whatever process drives the outbursts is sensitive to changing conditions such as the amount of gas available, or the state of the jet and accretion flow, even while the overall timescale remains remarkably stable. Beyond the optical band, observations during major outbursts reveal correlated changes at other wavelengths. Although the correlations are not always simple, one-to-one matches. In some cycles, radio emission from the compact core and from emerging jet components increases after the optical peak, suggesting that disturbances propagate outward along the jet. X-ray observations sometimes show enhanced emission near the times of optical flares, while in other cases the X-ray response is muted or delayed, reflecting the complex interplay of particle acceleration and cooling in different regions. Polarization measurements during outbursts often show swings in both degree and angle, pointing to significant reconfigurations of magnetic fields as new emitting regions brighten and fade. All of these pieces add depth to the picture painted by the optical light curve, but the optical record remains the backbone because of its long temporal coverage. When the entire light curve is viewed as a whole from the earliest plates through successive cycles of double outbursts to the most recent high cadence observations, OJ-287 appears as a system with a built-in rhythm on decadal timescales, overlaying the faster irregular flickering typical of blazars. Each time the source enters a new active phase, observers now anticipate that the brightness may climb toward another major outburst, and they prepare to capture it with as many instruments as possible. adding new points to the ever-lengthening curve. The combination of archival and modern data transforms what once was a scattered set of brightness estimates into a coherent history in which the timing of past events can be reconstructed, and future active intervals can be projected with some confidence within the uncertainties imposed by the quasi-periodic nature of the process. For astronomers, this long-structured light curve acts as a precise chronicle of how the central engine of OJ287 behaves over timescales much longer than a human career, providing both a constraint and a challenge for any physical model that seeks to explain how a distant active nucleus can sustain such a stable, yet subtly changing pattern of powerful outbursts across more than a century of observation. For many years after OJ287 is recognized as a powerful active galactic nucleus, the standard picture used to interpret its behavior involves a single, very massive black hole sitting at the center of the host galaxy, surrounded by an accretion flow and launching a relativistic jet that points almost toward Earth. This picture matches what is known from many other active nuclei and blazars, where a lone central black hole with a mass of millions to billions of times the mass of the Sun feeds on infalling gas and converts gravitational energy into radiation and jet power. Within this framework, the rapid irregular variability seen on short timescales in OJ287 is understood as the natural outcome of changes in the accretion rate turbulence in the flow shocks propagating along the jet and variations in magnetic fields. Numerical simulations of accretion disks and jets show that such systems can display complex flickering even when only one black hole is present, and this kind of explanation feels adequate for many blazars. When the long-term light curve of OJ287 becomes clearer, however, with its repeated strong double outbursts separated by intervals of about 12 years, the single black hole framework begins to face a more specific challenge. The pattern seems to suggest some kind of regular clocker process that resets on a decadal timescale and produces two major bursts in relatively quick succession each time. In a single black hole scenario, several ideas are proposed to account for this. One suggestion is that the accretion disk around the central black hole may undergo thermal or viscous instabilities that build up over years and then release energy in a burst somewhat like a reservoir that fills and occasionally overflows. Another possibility is that the inner disk or jet axis may precess, meaning that it slowly wobbles, and that the times when the jet points slightly closer to the line of sight correspond to periods of enhanced brightness. Still, another idea is that large-scale waves or spiral patterns in the disk might periodically channel more gas inward, leading to brighter phases. These models can sometimes reproduce aspects of the observed curve, especially if the parameters are adjusted carefully, but they tend to struggle with the repeated double peak structure and with the long-term consistency of the timings over many decades. As more cycles are added to the record, the apparent regularity of the major events becomes harder to dismiss as a coincidence. This prompts some researchers to consider whether an orbital motion might be involved, since orbits naturally introduce repeating timescales. In the broader field of galaxy evolution, it is already known that galaxies often merge, and that their central black holes can form pairs when their host galaxies combine. Observations of some galactic nuclei show signs of dual or offset cores, and theoretical models predict that binary supermassive black holes should form frequently, even if they are difficult to detect directly, because the scales involved are so small compared with the size of the galaxy. Against this background, a number of teams begin to explore the idea that the core of OJ287 might contain not just one supermassive black hole, but two in orbit around their common center of mass. In this picture, the more massive object would sit near the center of the accretion disk, while a lighter companion would travel on an elongated path that carries it through or close to the disk twice per orbit. Each time the secondary black hole plunges through the disk, it would disturb the surrounding gas, heat it, and trigger an outburst of radiation that could appear as one of the bright optical peaks seen in the light curve. The two crossings per orbit would then correspond to the double outbursts, and the orbital period would set the overall timescale of roughly 12 years between successive pairs. Early versions of this binary model are simple and use idealized assumptions about the disk structure and orbit, but they already offer a natural way to connect an orbital clock to the observed pattern. At first, the idea of a binary black hole at the heart of a blazar like OJ287 meets some skepticism because there are other systems in which single black hole models seem to suffice, and because the detailed physics of disk impacts and jet response is complex and uncertain. Some researchers argue that disk instabilities or jet precession could still explain the data if more parameters are considered, and the debate plays out in papers and conferences as new observations are added. Rather than being decided by a single measurement, the question is addressed gradually as the improved monitoring constrains the timing of outbursts more precisely and as theoretical models evolve. One important development is the move toward predictive modeling. Instead of only fitting past light curves, some versions of the binary model are used to forecast the approximate times of future major outbursts based on an orbit that takes into account the gravitational interaction between the black holes and corrections from a theory of gravity called general relativity. When subsequent monitoring campaigns find outbursts near the predicted times, confidence in the binary interpretation grows, even though the exact shapes and amplitudes of the flares still vary and remain challenging to model in detail. At the same time, refinements to the single black hole scenarios struggle to produce predictions that match the long baseline data as well as the binary models do. Another factor that strengthens interest in the binary hypothesis is its connection to other areas of astrophysics. If OJ287 indeed hosts a close pair of supermassive black holes, then its orbit should slowly shrink over time as the system loses energy, partly through interactions with surrounding gas and stars and partly through the emission of gravitational waves, which are ripples in the curvature of space-time produced by accelerating masses. Although the gravitational waves from such a pair would oscillate too slowly to be detected by current ground-based interferometers, they could contribute to the low-frequency background probed by pulsar timing arrays, and OJ287 could serve as a case study for how such binaries evolve. In this way, the efforts to model its light curve link the study of active galactic nuclei with the emerging field of gravitational wave astronomy. Over the years, as more cycles of outbursts are observed, and as more sophisticated simulations are carried out, a consensus begins to form that a binary black hole model offers the most coherent explanation of the long-term behavior of OJ287, while still acknowledging that uncertainties remain in the exact parameters such as the masses of the two black holes, the detailed structure of the accretion disk, and the microphysics of how disk crossings translate into radiation in different wave bands. The shift from a single black hole interpretation to a binary hypothesis is not abrupt but gradual, guided by the accumulation of evidence and by the requirement that any successful model must account for more than a century of structured variability. In the end, the central engine of OJ287 comes to be viewed not as a solitary massive black hole, but as a dynamic pair moving through a shared envelope of gas and magnetic fields, a pair whose orbital dance leaves a long sequence of timed imprints in the light that reaches Earth. In the current understanding of OJ287, the long sequence of timed outbursts and the broader properties of the active nucleus point toward a central system that is not built around a single supermassive black hole, but around a pair with one member enormously more massive than the other. The more massive object, often called the primary, sites close to the center of the host galaxy and anchors the accretion flow whose radiation and jet dominate the emission that is recorded. Models that fit the timing of the strongest optical outbursts together with constraints from the brightness of the nucleus and from general relationships between galaxies and their central black holes indicate that this primary has a mass of order tens of billions of times the mass of the Sun. This places it among the most massive black holes currently inferred in the universe, far heavier than the black hole at the center of the Milky Way, which has a mass of only a few million times the mass of the Sun, and heavier even than many central black holes in bright giant elliptical galaxies. Because such large masses are derived from indirect methods, they carry uncertainties and different modelling approaches may favour slightly different values, but they agree that the primary in OJ287 lies at the extreme upper end of the known distribution of supermassive black hole masses. Surrounding this primary is a very hot luminous accretion disk of gas and a pair of jets, one of which is pointed roughly toward Earth and gives the system its blazar character. Within this environment moves the lighter companion black hole, the secondary, whose presence is inferred primarily from the structured pattern of the outbursts and from the success of orbital models in reproducing their timing. The secondary is still a supermassive black hole in its own right, with a mass estimated to be in the range of hundreds of millions of times the mass of the Sun. This mass is comparable to, or larger than, the central black holes of many ordinary galaxies, yet in the context of OJ287, it is the smaller partner with a mass perhaps 100 times lower than that of the primary. As with the primary, the precise value depends on the details of the model, but the broad picture of a very unequal pair is robust. The large mass contrast means that the center of mass of the system lies close to the primary, so the primary moves only slightly in response to the mutual gravitational pull, while the secondary traces a wider path through the shared gravitational field. The orbit of the secondary around the primary is not a simple circle, but an elongated ellipse with one part of the path bringing the secondary relatively close to the primary, and another carrying it much farther away. In basic orbital terms, the point of closest approach is called pericenter, and the farthest point is called apocenter, and for OJ287 descriptions of the orbit indicate a high eccentricity, meaning a strongly stretched shape. At pericenter, the secondary passes through the inner regions of the accretion disk surrounding the primary, or at least through a region where the gas density is high enough that the passage of the black hole significantly disturbs it. Farther out near apocenter, the secondary moves through a more diffuse environment, where the gas is thinner and the gravitational field is weaker, and its influence on the disk and jet is correspondingly milder. The time it takes for the secondary to complete one full circuit around the primary, measured in the rest frame of the system, corresponds to the decadal timescale seen in the optical double outbursts, so that each orbit carries the secondary through two key locations where it can interact strongly with the disk. Because of the enormous masses involved, the characteristic orbital speeds near pericenter are a significant fraction of the speed of light, and the gravitational field near the primary is extremely strong. Under such conditions, the motions cannot be described accurately by the simple equations that govern planetary orbits in the solar system, which are based on Newtonian gravity alone. Instead, the trajectory must be calculated using the framework of general relativity, which takes into account how mass and energy curve space and time. Calculations in this framework show that the orbit is not perfectly repeating, but evolves slowly so that the shape and orientation of the path change slightly over many cycles. Even modest changes in the orbit can alter the times at which the secondary passes through dense regions of gas, and this sensitivity allows the sequence of outburst times to act as a detailed record of the binary motion. In the binary picture, the timing of the optical flares effectively measures the times of disk crossings, and by adjusting the mass of the primary, the mass of the secondary, and the initial shape and orientation of the orbit, theorists can seek a solution in which the computed crossing times match the recorded peaks as closely as possible. The fact that a consistent set of parameters can reproduce many of the major outbursts across more than a century of data is one of the reasons why the unequal mass binary model is widely discussed and applied to this source. It is important to note, however, that the binary is not an isolated pair in empty space. It is embedded in the dense central region of a galaxy surrounded by gas in the accretion disk, by hotter gas in a more extended atmosphere, and by stars that move in the combined gravitational field of the black holes and the stellar mass. All of these components can influence the orbit over long times. For example, dynamical friction with surrounding stars and gas can take energy from the binary and cause the separation to decrease, while torques from asymmetric gas distributions can alter the orientation of the orbit. At the same time, the motions of the black holes influence the gas, stirring it, shocking it, and occasionally compressing it enough to enhance its radiation. The present configuration of the pair is therefore the outcome of a long evolutionary history, likely involving one or more galaxy mergers that brought the two black holes together in the first place. In broad terms, when two galaxies of comparable size merge, their central black holes sink toward the common center of the new system under the action of dynamical friction and form a bound pair. Over time, the separation can shrink further as the pair interacts with stars and gas in its surroundings. In OJ287, the small separation inferred from the orbital period and the large masses suggest that the system is already in a relatively late stage of this evolution, with the two black holes orbiting at distances far smaller than the size of the surrounding galaxy, but still much larger than their own event horizons. Even at this stage, the gravitational field in the inner region is dominated by the primary and the secondary, can be thought of as moving through the curved space near a massive central object, following a path that is determined both by initial conditions and by ongoing interactions with its environment. Within this setting, the enormous mass of the primary ensures that its accretion disk is very extended and that its gravitational influence reaches far, while the presence of the secondary provides a repeating external perturbation that can disturb the disk at predictable intervals. The lighter companion thus plays a role out of proportion to its mass in shaping the time structure of the radiation that escapes, because each close passage can leave an imprint in the light curve that is visible billions of years later when the photons reach Earth. The masses, separation and orbital period together define an inner system that is extremely compact on galactic scales, yet vast in terms of human units, a dynamic pair of supermassive black holes whose mutual orbit underlies the decadal rhythm of the brightest outbursts in OJ287, and whose slow evolution over many cycles gradually alters the timing and possibly the character of the events that astronomers record. The orbit of the secondary black hole around the primary in OJ287 is not a simple fixed ellipse that repeats identically with each cycle, but a path that slowly turns and changes under the influence of strong gravity, making the system a natural laboratory for observing how motion unfolds in a deeply curved region of space. At the most basic level, the secondary follows an elongated orbit, spending much of each cycle far from the primary and then rushing through pericenter, the point of closest approach where its speed and the strength of the gravitational field both become very large. In a purely Newtonian description, such an orbit would trace out the same closed ellipse over and over again, always returning to the same pericenter direction after a fixed period. In OJ287, the masses involved and the compactness of the orbit mean that this simple picture no longer holds. The immense mass of the primary, measured in tens of billions of solar masses in some models, and still at least many billions of solar masses in others, curves space-time so strongly that the secondary's path precesses meaning that the ellipse slowly rotates within its own plane. As a result, each time the secondary completes one revolution, it returns to a slightly different pericenter direction, and the orbit does not close but instead sweeps out a rosette pattern over many cycles. The amount of this precession per orbit is large compared with familiar examples, such as the slow rotation of Mercury's orbit in the solar system. For OJ287, models that fit the timing of outbursts indicate that the pericenter direction advances by several tens of degrees in a single 12-year cycle, so that after only a few orbits, the long axis of the ellipse is turned through a large angle. This rapid advance is a signature of strong field general relativity, the theory that describes how mass and energy curve space and time. In that theory, the gravitational field around a massive compact object such as a black hole differs from the Newtonian inverse square law, especially close to the object, and this difference shows up in the motion of orbiting bodies as a precession of the orbit. If the primary also spins, which is expected for a black hole that has grown through accretion, then additional effects appear, such as frame dragging, in which the rotation of the black hole drags nearby space around with it. This spin-induced effect, sometimes called lens-Thirring precession, can cause the orbital plane itself to precess, adding further complexity to the path. The full description of the motion therefore requires not just a single correction, but a hierarchy of corrections to the Newtonian orbit, often expressed in a systematic expansion known as a post-Newtonian series. For OJ287, theorists use such an expansion to high order, including terms that account for the strong curvature near the primary and for the back reaction from gravitational wave emission. In practical terms, this means solving equations of motion that incorporate general relativity up to several levels beyond the leading correction, and then adjusting the parameters of the system so that the calculated times at which the secondary crosses the accretion disk match the observed times of major optical outbursts. The success of this exercise is one of the striking features of OJ287. When a model is tuned using older flares and then used to predict the future times of disk crossings, which in this picture produce the brightest optical outbursts. The predicted times for some recent events have matched observations to within a fraction of a year or even better. This is remarkable given that the outbursts are produced by gas dynamics that are not perfectly understood by a disk whose structure may vary, and by observations that themselves have finite timing uncertainties. The fact that a general relativistic orbit can nonetheless reproduce the broad sequence of flares over more than a century is taken as strong evidence that the secondary really is following a precessing shrinking path around a massive primary, and that general relativity describes this motion well, at distances of only a few tens of gravitational radii from the central object. Another key element of the orbit is its gradual decay. As the two black holes move around one another, they emit gravitational waves, ripples in the curvature of space-time that carry away energy and angular momentum. In the case of OJ287, the frequency of these waves is very low, far below the range of ground-based detectors, but their cumulative effect over many orbits is to reduce the orbital period and shrink the semi-major axis. The light curve with its long series of timed flares provides a way to measure this shrinking indirectly, because if the orbit is losing energy, the times between successive disk crossings will change in a predictable way. By comparing observed flare times with those predicted by models that include gravitational wave losses, astronomers can infer how quickly the orbit is decaying. Calculations suggest that the system is indeed losing energy at a rate consistent with general relativity, and that if current conditions persist, the two black holes may spiral together and merge on a timescale of roughly 10,000 years in the frame of the system, although this estimate carries uncertainties linked to the exact masses and to the distribution of gas and stars in the region. In addition to gravitational wave emission interactions with the surrounding accretion disk and with stars in the nuclear region can also influence the orbit. Gas torques from a non-uniform disk can exchange angular momentum with the binary, either hastening or slowing its inward migration, and dynamical encounters with stars can extract energy from the binary by ejecting stars to larger orbits. These processes are more complex to model than the clean radiation of gravitational waves because they depend on the detailed structure and distribution of matter around the black holes. In OJ287, the dominance of the accretion disk and jet in the emission suggests that gas plays an important role in the inner region, but the exact balance between gas-driven evolution and gravitational wave-driven evolution remains an active topic of research. Even with these uncertainties, certain broad conclusions are robust. The orbit is highly eccentric, bringing the secondary much closer to the primary at pericenter than at apocenter. The pericenter distance is only a few tens of times larger than the radius of the primary's event horizon, so that the secondary samples the strong field region near the central black hole. The pericenter direction precesses by many tens of degrees per orbit, far more than in any system governed purely by Newtonian gravity. The period decreases slowly as energy is carried away by gravitational waves, and this decrease is detectable in the timing of the observed flares. Together, these properties make OJ287 a rare example of a supermassive binary whose orbital motion can be tracked in detail and used to test theories of gravity in a regime intermediate between the relatively weak fields of the solar system and the very strong rapid dynamics of stellar mass binaries observed by current gravitational wave detectors. From the point of view of the light curve, the precessing shrinking orbit shows up as slight shifts in the times when the secondary encounters dense regions of gas in the accretion disk, and these shifts accumulate over decades into measurable differences between when an outburst would occur in a simple, non-precessing orbit and when it actually occurs. Each new cycle of outbursts thus refines the orbital solution and tightens the constraints on the mass's eccentricity and relativistic parameters of the system. The present models are already consistent with the data at a level that strongly supports general relativity as the correct description of gravity in this context, while still leaving room for improved measurements and more detailed modelling as future observations add new points to the long sequence. In this way, the orbit of the secondary around the primary in OJ287 is not only a path traced in curved space, but also a sequence of timed markers embedded in the light that reaches Earth, tracing a slowly turning, gradually shrinking loop around one of the most massive known black holes, and encoding in its rhythm the combined effects of gravity relativity and the surrounding environment. Around the primary black hole in OJ287 stretches a broad luminous structure of gas known as an accretion disk, a flattened flow of matter that orbits in nearly circular paths while gradually spiraling inward under the pull of gravity and the action of internal friction. This disk forms because gas captured from the host galaxy or delivered by mergers carries angular momentum, the property associated with rotation, and cannot fall directly into the black hole. Instead, it settles into a rotating configuration where each ring of gas orbits at a speed set by the balance between gravity and centrifugal forces. In the simplest idealized picture, the disk is geometrically thin, meaning that its thickness is small compared with its radius, and optically thick, meaning that photons scatter many times before escaping, so that the emission from each radius resembles that of a hot surface, whose temperature depends on how much energy is released there. In reality, the disk around the primary in OJ287 is influenced by many factors, including the very large mass of the black hole, the rate at which gas is supplied the presence of strong magnetic fields, and the interaction with the surrounding jet and environment, but the basic structure still follows this picture of a rotating, slowly draining reservoir. Near the outer edge of the disk, at distances that may reach light months, or even light years from the center, the gas is relatively cool by accretion standards, perhaps only a few thousand degrees Celsius, and its emission lies mainly in optical and infrared wavelengths. Moving inward, the gravitational potential well deepens and the orbital speed increases. Gas in these regions loses energy and angular momentum through small-scale turbulence and magnetic stresses, which can be thought of as an effective viscosity, and as it does so, it transfers angular momentum outward and drifts inward. The energy lost in this process is converted into heat and radiated away. As a result, the temperature of the disk rises toward the center, reaching tens of thousands of degrees Celsius or more in the innermost regions where most of the gravitational energy is released. There, the emission shifts toward ultraviolet and even soft X-ray wavelengths. Although in a system like OJ287, where jet-related non-thermal emission is very strong, the direct thermal signature of the inner disk can be partly masked. The vertical structure of the disk, meaning how density and temperature vary from the midplane to the upper layers, is shaped by a balance between gravity pulling gas toward the midplane and pressure gradients pushing outward. At each radius, gas near the midplane is densest and does most of the carrying of mass inward, while higher layers are more rarefied and can be heated to higher temperatures by radiation and by magnetic activity, forming a kind of hot corona above and below the cooler bulk of the disk. This corona can scatter photons to higher energies, contributing to X-ray emission that varies with the state of the accretion flow. Embedded within the disk are magnetic fields amplified by differential rotation and turbulence in a process known as a dynamo. These fields thread the gas and mediate the transfer of angular momentum, and they may also connect to the rotating black hole and to the base of the jet, providing channels through which rotational energy can be extracted and fed into outflows. On larger scales, the disk is not perfectly smooth. Variations in the rate at which gas is supplied from the host galaxy interactions with orbiting masses and internal instabilities can all create regions where the surface density and temperature differ from their average values. Spiral-like patterns, rings or clumps may form drift and dissolve as the flow adjusts. Some sections of the disk may be slightly thicker or puffed up, especially where radiation pressure, the pressure exerted by intense light, becomes comparable to or exceeds the pressure from the gas itself. In those zones, the vertical support of the disk changes and the thickness can increase, altering how light escapes and how the disk interacts with its surroundings. The immense mass of the primary black hole in OJ287 means that the gravitational radius, the characteristic scale associated with its event horizon, is very large in absolute terms, perhaps comparable to the size of the solar system or larger. Yet in units of this radius, the disk still extends over only a few tens of thousands of gravitational radii, so that even gas at what seems like a large physical distance remains relatively close in gravitational terms. This compactness ensures that orbital periods in the inner disk are short, ranging from days to weeks, and that the dynamical timescales on which the disk can react to disturbances are correspondingly rapid. When a patch of the disk is heated or disturbed, it can brighten and fade on timescales that reflect these orbital periods, and the local cooling time adding finer structure to the longer-term variability driven by global changes in the flow or by the motion of the secondary. The radial profile of the disk, that is how quantities such as surface density, temperature and pressure vary with distance from the center, determines not only how much radiation is emitted at each wavelength, but also how much gas is available at different radii to participate in interactions. In the outer regions, where the density may be lower but the area is large, even modest changes in conditions can alter the total amount of mass flowing inward over many years. In the inner regions, where the density and temperature are higher, small changes can have large effects on the luminosity and spectral shape. OJ287 is observed as a bright blazar whose emission is dominated by jet processes, but the underlying accretion disk still provides the fuel and sets boundary conditions for the jet. The rate at which mass flows through the disk toward the primary governs how much gravitational energy is available to be converted into radiation, and outflows and changes in this rate can modulate the baseline brightness of the system and the frequency and strength of episodes of enhanced activity. The disk also serves as the medium through which forces are transmitted between different parts of the system. Waves and disturbances excited at one radius can propagate inward or outward, carrying angular momentum and energy. In the context of a binary, where a secondary black hole orbits within or around the disk, its gravitational pull can raise waves and warp the disk, creating non-axisymmetric features that evolve over time. Although the detailed pattern of these features in OJ287 remains uncertain and depends on the exact parameters of the system, general studies of disks in binary systems show that such interactions can lead to the opening of gaps, the formation of eccentric rings, and the concentration of gas in certain regions. These structural changes feed back on the orbit and on the way the disk radiates. In the innermost zones close to the radius within which stable circular orbits are no longer possible, gas plunges rapidly into the black hole. This region is often called the inner edge of the disk, and its exact location depends on the spin of the black hole. If the primary spins rapidly in the same direction as the disk, the inner edge can lie closer to the horizon, allowing more gravitational energy to be released in the disk. If the spin is lower or misaligned, the inner edge lies farther out. For OJ287, attempts to estimate the spin of the primary from modelling of the light curve and jet properties suggest that it may be high, but uncertainties remain, and the inner structure of the disk is not yet mapped in detail. Even so, the presence of a hot, dense inner region is clear from the luminosity of the system and from the need to supply sufficient power to the jet. The combined effect of all these layers, from the relatively cool outer disk to the very hot inner edge and overlying corona, is to produce a multi-temperature, multi-component source of radiation and a structured reservoir of gas whose properties change gradually over time. The light that escapes from the disk carries information about its temperature profile and about the ongoing balance between heating and cooling, while the way the disk responds to perturbations offers clues about its viscosity, density and magnetic state. In OJ287, direct observation of the thermal disk emission is complicated by the strong non-thermal continuum from the jet, but by studying the spectral energy distribution across many wavelengths, and by comparing with models of accretion onto very massive black holes, astronomers infer that a luminous extended disk surrounds the primary and feeds it at a rate that, while high by ordinary standards, remains below the maximum level at which radiation pressure would completely disrupt the inflow. This disk is the quiet but crucial foundation of the active nucleus, transforming inflowing gas into heat, light and mechanical power and providing both the fuel and the structure within which other processes in the central region unfold. In the binary interpretation of OJ287, the brightest optical flares arise when the lighter secondary black hole plunges through the dense accretion disk surrounding the primary, converting orbital energy into heat and radiation as it disturbs gas along its path. On most days of its long orbit, the secondary moves through regions where the gas density is modest, and its influence on the disk is relatively gentle, raising waves and warps that evolve over many orbits. Near pericenter, however, the orbit carries it inward to radii, where the disk is thick and hot, and there the encounter becomes far more dramatic. The secondary does not skim smoothly along the top of the disk, but crosses the disk plane, entering from one side, passing through the mid-plane and emerging on the other side. In doing so, it creates a narrow, rapidly moving region of intense gravitational disturbance that compresses and shocks the gas in its vicinity. Gas near the crossing point is accelerated, heated to very high temperatures, and displaced from its original orbits, leaving behind a trail of disturbed material that gradually settles or flows inward. The immediate energy release in the gas is dominated by shock heating. As the secondary sweeps through, it exerts a strong tidal force that stretches and squeezes the gas, producing shock fronts, in which kinetic energy is converted into thermal energy. Temperatures in these shocked regions can rise far above the local equilibrium set by ordinary viscous dissipation in the disk, and the gas responds by radiating more intensely, especially in optical and ultraviolet wavelengths, where many of the observed flares are prominent. Because the disk is optically thick, the energy deposited by the shock does not escape instantly, but diffuses outward through the surrounding gas, spreading the brightening over weeks or months. This diffusion, combined with the time it takes for the heated gas to expand and cool, gives the flares their characteristic rise and decay times, which are longer than the brief duration of the crossing itself. In simple terms, the passage of the secondary acts as a sudden input of energy into a compact region of the disk, and the flare is the response of the disk as it radiates that energy away. In models of OJ287, each major optical outburst corresponds to one such disk crossing. Because the orbit is eccentric, the secondary intersects the disk at two distinct points, during each revolution, one on the way in and one on the way out, leading naturally to a pair of crossings and thus to a pair of major flares per orbit. The geometry of these encounters is not symmetric. The secondary meets gas that has different densities, temperatures, and orbital velocities at the two crossing points, and the angle at which it passes through the disk can also differ. As a result, the two flares in each pair tend to have different shapes and amplitudes. In some cycles, the first flare rises sharply and reaches a high peak, while the second is broader and somewhat fainter. In others, the second flare may be more complex with multiple sub-peaks, as the disturbed gas interacts with existing structures in the disk. Hydrodynamic simulations, which follow how gas responds to the gravitational pull and motion of the secondary, reproduce this kind of variety. They show that the shocked gas can form expanding plumes above and below the disk plane, that these plumes can cast temporary shadows or produce anisotropic emission, and that the detailed light curve depends sensitively on the local conditions at the time of impact. Despite these complications, the overall pattern of double flares with a roughly decadal spacing between pairs emerges naturally from a binary with two disk crossings per orbit, and this is one of the reasons the disk impact model is attractive. The energy scale of these events illustrates the extreme environment near the primary. The mass of the gas intercepted by the secondary during a single crossing is small compared with the total mass of the disk, yet the relative velocities are so high and the gravitational field so strong that the energy deposited is almost sufficient to temporarily increase the luminosity of the nucleus by a large factor. Even a small fraction of the orbital energy converted into radiation can power a flare brighter than an entire ordinary galaxy of stars, at least for the duration of the event. The heated gas then cools and in many models settles back toward the disk, though some fraction may be ejected into a more extended atmosphere or carried inward toward the primary. The exact partition between these outcomes remains uncertain and depends on details of the disk structure, the cooling rate, and the magnetic field configuration. Observationally, the disk impact picture finds support in the timing and spectral behavior of the major flares. The largest optical outbursts tend to occur near the predicted times of disk crossings in general relativistic orbital models, and their spectra often show a strong thermal component that can be described as a hot blackbody, like emission with temperatures of tens of thousands of degrees Celsius. This thermal signature is distinct from the non-thermal synchrotron continuum that dominates the quiescent and moderately active states, and is broadly in line with expectations for shock-heated gas in the disk. During some flares, the color of the source becomes bluer, indicating a higher characteristic temperature, and then gradually reddens as the flare decays, mirroring the cooling of the shocked material. In some cycles, observers detect enhanced emission in ultraviolet bands that are especially sensitive to hot gas, reinforcing the idea that disk heating plays a central role. At the same time, the complex environment in the central region of OJ287 ensures that not every feature in the light curve maps cleanly onto a single disk crossing. Smaller flares and irregular variations continue to occur between the major outbursts driven by fluctuations in the accretion flow and by jet-related processes. Even during a major flare, the thermal component from the disk must compete with variable non-thermal emission from the jet, which can brighten or fade on its own timescales. This interplay can blur the simple picture in which each crossing produces an isolated, easily recognizable thermal pulse. In practice, astronomers disentangle these components by examining the spectral energy distribution over many wavelengths and by tracking how the polarization behaves. Thermal radiation from the disk impact region is only weakly polarized, while synchrotron radiation from the jet is strongly polarized and shows rapid changes in polarization angle. During some of the predicted impact flares, the polarization degree decreases, while the total flux increases, suggesting that an additional, less polarized thermal component is diluting the more polarized jet light. This behavior is consistent with the idea that a luminous, relatively unpolarized disk flare is superposed on a variable jet continuum. The cooling and hydrodynamic evolution of the shocked gas also influence the flare profile. In regions where the local density is high and the gas is optically thick, photons must scatter many times before escaping, and the flare decays slowly as the energy leaks out. In less dense regions or at higher altitudes above the disk, where the optical depth is lower, radiation can escape more quickly, leading to a faster decay. The secondary's passage can also trigger waves that propagate along the disk, redistributing mass and angular momentum over larger scales. These waves may not themselves produce dramatic brightening, but they can alter the background state of the disk, changing how it responds to subsequent disturbances or to steady inflow from larger radii. In long-term models, this feedback means that each disk crossing does not occur in an identical environment. Instead, the secondary repeatedly encounters a disk whose structure has been modified by previous impacts and by ongoing accretion, and this evolving context helps to explain why the flares differ in detail from cycle to cycle, even though they follow a broadly repeated pattern. A further layer of complexity comes from the vertical structure of the disk. and from any pre-existing warps or misalignments between the disk plane and the orbital plane of the secondary. If the planes are not perfectly aligned, the secondary may pass through the disk at different heights in different cycles, encountering different column densities of gas and producing flares of different strengths. Warps and bends in the disk can also change the local orientation of the gas with respect to the orbit, altering the geometry of the shock and the direction in which heated material is thrown out. These subtleties mean that matching every detail of every flare is beyond current models, yet the basic picture remains robust. A massive primary surrounded by a luminous disk and a lighter secondary that periodically punctures that disk, generating strong thermal-dominated flares whose timing and approximate strength align with the patterns seen in more than 100 years of observations. Remaining uncertainties concern not the existence of these impacts, but the precise mapping between impact parameters and observed properties. For example, it is still an active question how much of the shock-heated gas moves inward toward the primary, how much expands into a hotter, more tenuous corona, and how much is driven outward into the surrounding medium, and how each of these channels contributes to emission at different wavelengths. Future observations that capture full spectral and polarization information throughout multiple flares combined with more detailed numerical simulations of disk impacts in a realistic magnetized environment are expected to refine this picture further. For now, the repeated thermal outbursts in OJ287 stand as strong evidence that the orbiting secondary does not merely move silently through empty space, but actively reshapes the inner environment of the primary by punching through its accretion disk, leaving behind luminous scars in the form of bright flares that can be seen across billions of light years. From the central regions of OJ287, close to where the accretion disk around the primary black hole releases most of its energy, narrow oppositely directed outflows of plasma emerge and extend far into space, forming a pair of jets that carry matter magnetic fields and radiation away from the nucleus at speeds close to the speed of light. These jets are not gentle breezes but highly collimated streams confined to a narrow opening angle by a combination of magnetic and pressure forces. In the simplest picture, magnetic fields anchored in the rotating disk and perhaps in the spinning black hole itself twist into a helical configuration as the plasma orbits and falls inward. This twisting generates tension along the field lines, much like tension in a coiled spring, and that tension helps to accelerate particles outward along the rotation axis away from the disk plane. The result is a jet that emerges from each side of the central engine, one pointing roughly toward Earth and the other away into the opposite side of the host galaxy. The jet that points toward Earth plays a dominant role in what is observed because its radiation is focused by relativistic beaming, while the counter jet is much fainter and contributes little to the recorded emission. Inside the jets, particles, mostly electrons and possibly positrons, along with some heavier ions, move through magnetic fields at relativistic speeds. As they spiral around the field lines, they emit synchrotron radiation, a process that produces a broad spectrum of photons spanning radio-infrared and optical wavelengths. In OJ287, this synchrotron component is strong and variable, providing much of the non-thermal continuum that defines its blazar nature. At the same time, the same population of high-energy electrons can scatter lower-energy photons to much higher energies in a process known as inverse Compton scattering, contributing to X-ray and gamma-ray emission. The seed photons for this scattering may come from the synchrotron radiation itself, from thermal emission from the accretion disk, or from external sources such as broadline region clouds or a dusty torus. And the relative importance of these contributions can change as conditions in the inner regions evolve. Because the jet moves at speeds close to the speed of light, special relativity alters how its radiation appears to an observer. In the rest frame of the plasma, the emission may be roughly symmetric, but in the frame of an observer lying close to the jet axis, the radiation is concentrated into a narrower cone around the direction of motion. This beaming effect, often described in terms of a Doppler factor that depends on the jet speed and orientation, increases the apparent brightness of the jet by a large factor, and compresses timescales so that variations intrinsic to the plasma appear faster. In OJ287, the alignment is such that the forward jet points within a small angle of the line between the galaxy and Earth, so the observed emission is strongly amplified. This amplification explains why the jet continuum can outshine the combined starlight of the host galaxy, and why relatively small disturbances in the inner regions can lead to noticeable changes in brightness over days or weeks. Polarization provides another window into the jet. Synchrotron radiation is naturally polarized because the electrons follow ordered paths around magnetic field lines, and the degree and angle of polarization carry information about the field geometry and the structure of the emitting region. In OJ287, optical and radio observations show that the polarization is often high and that both its degree and position angle vary with time. During quiet states, the polarization may be moderate and relatively stable, reflecting a mixture of ordered and tangled fields. During flares, the polarization can increase or undergo smooth rotations, suggesting that new, more ordered structures such as shocks or magnetic knots are passing through the region that dominates the emission. These patterns support a picture in which the jet contains moving features sometimes called components, or blobs that propagate outward and evolve as they travel. Very long baseline interferometry, which combines radio telescopes across continents to achieve extremely high spatial resolution images. The jets of many blazars as narrow structures extending across distances of parsecs or even kiloparsecs. For OJ287, such techniques reveal a compact core and jet-like extensions on milliarcsecond scales, corresponding to parsec-scale structures at its distance. Some features appear to move along the jet with apparent speeds that exceed the speed of light, a phenomenon known as superluminal motion. This effect does not violate relativity, but arises from projection and light travel time effects when a disturbance moves at near light speed close to the line of sight. The detection of such apparent superluminal components confirms that the jet in OJ287 indeed carries plasma at relativistic speeds, and that its axis lies close to the observer's direction. Along the length of the jet, shocks can form when faster-moving plasma catches up with slower material ahead, compressing and heating the gas and temporarily enhancing the local emission. These shocks are candidate sites for particle acceleration, where some fraction of the particles are pushed to even higher energies, steepening or flattening the local energy distribution and changing the spectral slope of the emitted radiation. When a new shock forms near the base of the jet, it can cause a flare that first appears at high frequencies such as optical or X-ray bands, and then propagates to lower frequencies as the shocked region moves outward and expands. This pattern of frequency-dependent delays has been seen in many blazars and is consistent with multi-wavelength monitoring of OJ287, where some optical flares are followed by radio brightening after a delay. The jet does not exist in isolation but interacts with the medium around it. Close to the nucleus, it passes through a region containing gas clouds, dust, and possibly a broad line region of ionized gas. The intense radiation and mechanical power of the jet can heat, ionize, or sweep aside this material, carving a path through the inner galaxy. Farther out on scales of hundreds or thousands of parsecs, the jet may encounter denser interstellar gas and form larger scale structures such as radio lobes or hotspots. Although in OJ287 the brightness of the compact core and the large distance make such extended emission more difficult to detect, even if the extended structures are faint, their existence can be inferred from the overall radioluminosity and from analogies with better resolved systems. Through these interactions, the jet deposits energy and momentum into the host galaxy and its surroundings, a process known as feedback, which can heat gas, regulate star formation, and contribute to the broader evolution of the galaxy. In the inner regions that are the focus here, the jet is also intimately connected to the state of the accretion disk, and possibly to the spin of the primary black hole. Theoretical models suggest that a rapidly spinning black hole threaded by strong magnetic fields can power especially strong jets, extracting rotational energy through processes that tap into the difference between the rotation of the black hole and the distant universe. The efficiency of this extraction depends on how the magnetic flux is accumulated near the horizon, and on the alignment between the spin axis and the disk. In OJ287, the high luminosity of the jet and its blazar character point to a configuration in which the magnetic flux near the primary is large and the spin is significant, although quantitative estimates carry uncertainties. Changes in the accretion rate or in the magnetic flux that reaches the inner regions can alter the jet power, leading to longer-term trends in the baseline brightness, and to changes in the frequency and amplitude of flares. The binary nature of the central system adds an additional layer of complexity, because the orbiting secondary can perturb the inner disk and perhaps the magnetic field configuration indirectly influencing the jet. For example, disk impacts that produce thermal flares may also change the supply of magnetic flux or plasma to the jet base, leading to correlated variations in jet emission. Some observations of OJ287 show episodes where optical flares with strong thermal components coincide with changes in polarization and in higher energy emission, hinting that disk and jet are responding together to disturbances triggered by the secondary. Untangling these connections remains an active area of study, but the basic picture is clear. The jet is not simply an independent structure, but a channel through which the central engine communicates with its surroundings, and in OJ287 that engine includes both a massive primary black hole and an orbiting companion. Across all these layers, from the magnetized plasma at the jet base to the parsec-scale structures imaged by radio arrays, the beaming of radiation along the jet axis governs what observers see. It makes the nucleus extraordinarily bright for its distance, compresses variability into shorter timescales, and magnifies the impact of relatively small changes in the inner conditions. It also means that OJ287 serves as a sensitive probe of processes that would otherwise be hidden, because the alignment between jet and line of sight places the observer in a privileged direction, where the central activity is projected almost directly toward the instruments collecting the light. In this way, the jets and their relativistic beaming are central to the blazar nature of OJ287, shaping its spectrum variability and polarization, and linking the physics of the accretion disk and binary orbit to the radiation that is recorded and analyzed. Around the binary black hole in OJ287 stretches a dense and layered environment of gas and stars, a compact nuclear region in which the gravity of the pair dominates the motions of everything nearby, and in which several different processes gradually drain energy from the orbit. On scales of a few light years or less, the primary sits at the center of an accretion disk, whose inner parts have already been described, but beyond this disk and partially overlapping with it lies a more diffuse, roughly spherical atmosphere of hot gas. This gas is heated by radiation from the disk and jet, by shocks driven into the interstellar medium, and by the cumulative effect of many supernova explosions from earlier generations of stars. It is tenuous compared with the dense mid-plane of the disk, yet still thick enough in an integrated sense that the secondary black hole feels its presence as it moves through the region. Each time the secondary passes through this gaseous background, it creates a wake, a trailing region where gas is gravitationally focused and pulled along. This wake exerts a drag force on the secondary, a process called dynamical friction, which slowly removes orbital energy and angular momentum. The effect is subtle on the timescale of a single orbit, but significant over many thousands of orbits, and it contributes to the gradual shrinking of the binary. Closer to the disk plane, the gas is cooler and denser, forming what can be thought of as a circumnuclear disk that extends beyond the main accretion structure. In this region, clouds of molecular gas and dust orbit the center at distances of tenths to a few light years, providing a reservoir that can feed the inner disk over long times. The presence of this gas is inferred from infrared emission, which indicates warm dust, and from spectral lines that show molecular transitions. This circumnuclear medium feels the combined gravity of the two black holes and responds by warping and twisting, especially if the orbital plane of the secondary and the angular momentum axis of the disk are not perfectly aligned. The secondary can raise spiral density waves in the outer disk, creating regions of enhanced gas density that in turn exert torques back on the orbit, exchanging angular momentum between binary and disk. In some models, these gas torques can hasten the inward migration of the secondary, while in others they can temporarily slow it depending on the distribution of material and the specifics of the interaction. Inside a few parsecs of the center stars also play an important role. The nuclear region of a massive galaxy is expected to contain a dense cluster of stars with many orbits crossing the central zones. Some of these stars move on elongated paths that carry them close to the binary, where their trajectories can be strongly perturbed. When a star passes within a certain distance of the pair, it can extract energy from the orbit through a gravitational slingshot effect, leaving the encounter on a wider orbit, or even being ejected from the nucleus, while the binary loses a small amount of energy and shrinks. Over time, many such interactions can erode the binary's orbital energy, a process sometimes described as the hardening of the binary. The rate at which this occurs depends on how efficiently stars are scattered into lost cone orbits that bring them close to the pair. If the supply of such stars is rich, interactions can be frequent. If it is depleted, the binary may temporarily stall at a separation where stellar encounters become rare. In a system like OJ287, the combination of a very massive primary and a dense surrounding cluster suggests that stellar interactions have already played a major role in bringing the two black holes to their present separation. The distribution of stars in this nuclear cluster is influenced in turn by the presence of the binary. Orbits that pass too close to the pair can be emptied as stars are ejected or tidally disrupted, leaving behind a core in the stellar density profile, a feature that is indeed seen in many massive elliptical galaxies. Farther out, stars move in a gravitational potential dominated by the combined mass of the black holes and the inner galaxy, and help to trace the overall mass distribution. Mixed into this stellar population are compact remnants such as white dwarfs, neutron stars, and smaller stellar mass black holes, which can also interact with the central pair, although their individual influence is small compared with that of the countless ordinary stars. While gas and stars provide mechanisms for exchanging energy with the binary, another channel operates that does not rely on surrounding matter at all. As the two black holes orbit each other, especially when they pass close at pericenter, their rapidly changing quadrupole moment generates gravitational waves, ripples in the curvature of space that propagate outward at the speed of light. These waves carry away energy and angular momentum, causing the orbit to shrink and the period to decrease. The efficiency of this radiation depends strongly on the separation and eccentricity of the orbit. For wide, nearly circular orbits, the energy loss per cycle is small, but for a highly eccentric orbit like that inferred in OJ2-87, the emission peaks strongly near pericenter, where the velocities and accelerations are highest. This means that most of the gravitational wave power is radiated in brief episodes each time the secondary swings close to the primary, much as most of the shock heating in the disk impact is concentrated near the crossing points. Over one orbit, the total energy radiated in gravitational waves is still a tiny fraction of the binding energy of the system, but over many orbits the cumulative effect becomes significant, leading to a measurable decrease in the orbital period. In OJ287, the long baseline of optical outburst timings acts as a sensitive clock for tracking this decrease. When theorists construct models that include gravitational wave losses according to general relativity, and compare the predicted times of disk crossings with the observed times of major flares, they find that the best-fitting models require a small but definite inward drift of the orbit. If the orbit were static, the times between successive crossings would remain constant, but in the data a slight shortening is seen consistent with energy being carried away by gravitational waves. This agreement between observation and theory provides one of the clearest pieces of evidence that supermassive black hole binaries, not just stellar mass binaries, radiate gravitational waves in line with general relativity, even though their waves are too low in frequency to be directly detected by current ground-based observatories. At the same time, the presence of gas and stars around the binary means that the measured drift reflects a combined effect. Gas torques can either reinforce or partially offset the shrinkage due to gravitational waves, and stellar encounters can add an additional source of energy loss, or in some configurations can even pump eccentricity and alter the distribution of energy between radial and tangential motion. The present orbit of OJ287 is therefore the result of all these influences acting together over long periods, with gravitational waves dominating at the smallest separations, and with gas and stars more important at earlier stages when the separation was larger. In rough terms, theoretical estimates suggest that for a pair with the masses inferred for OJ287, and with its current orbital period, the timescale for merger under gravitational wave emission alone is on the order of 10,000 years, a very short interval compared with the age of the universe, but still far longer than the span of human observations. This means that the orbit is shrinking perceptibly on century timescales, yet will not complete its inspiral for many thousands of years in the frame of the system. During this period, the binary continues to interact with its gaseous and stellar surroundings, stirring the nuclear region, and possibly influencing the rate at which new stars form there. The central potential well occupied by the pair acts like a deep basin into which gas can fall. Some of this gas becomes part of the accretion disk feeding the primary, while some may form stars in a compact nuclear disk or ring. Feedback from the jet and radiation heats, and sometimes expels gas, helping to regulate the balance between inflow and star formation. The presence of the secondary complicates these flows by periodically perturbing the gravitational field and by punching through the disk as described earlier, injecting heat and momentum into the gas. On somewhat larger scales, the jet carries energy out of the nucleus and into the host galaxy, and beyond, shaping the thermal and dynamical state of the circumgalactic medium. In this way, the binary not only evolves within its environment, but also contributes to reshaping that environment. Yet for the purposes of understanding OJ287, as a system, the key point is that the surrounding gas and stars, together with the emission of gravitational waves, provide a set of channels through which orbital energy is steadily drained. The process is slow in human terms, but rapid in cosmic ones, and the light curve with its timed flares captures this slow tightening of the orbit as slight shifts in the intervals between outbursts. Each new observation of a predicted flare refines the measurements of these intervals, and thus the inferred rate of energy loss, tightening the constraints on models of how gas stars and radiation combine, to guide a pair of supermassive black holes toward eventual coalescence in the heart of a distant galaxy. As the picture of OJ287, as a binary system with a powerful jet and a luminous accretion disk, becomes more detailed, coordinated campaigns that observe it across the entire accessible spectrum take on a central role, because they allow astronomers to test models against a wide range of independent signatures, rather than relying on a single band of light. In practice, this means bringing together optical telescopes that monitor brightness and color radio arrays that resolve and measure the jet ultraviolet and X-ray observatories in space that capture the high-energy output, and when possible, gamma-ray instruments sensitive to the most energetic photons. Each facility sees a different face of the same system, and by comparing their measurements in time and frequency, observers can build what is called a spectral energy distribution, which is a representation of how much energy the source emits at each wavelength or photon energy. For a blazar like OJ287, this distribution typically shows two broad humps, one at lower energies dominated by synchrotron radiation from the jet, and another at higher energies dominated by inverse Compton processes. The exact shape and height of these humps change between quiet states and outbursts, and the way they change provides clues to whether a particular flare is driven mainly by disturbances in the jet, by heating in the disk, or by a combination of both. During anticipated major outbursts scheduled on the basis of binary orbital models that predict disk crossing times, the observing strategy becomes especially dense. Optical telescopes of many sizes, including small robotic instruments and larger professional facilities, monitor the source nightly or even more frequently when possible, recording light curves in multiple filters to track both total brightness and color. At the same time, polarimeters measure how the degree and angle of polarization evolve, while radio arrays map the compact core and any emerging jet components on timescales of weeks to months. Space-based telescopes add ultraviolet and X-ray coverage, sometimes with intensive pointing campaigns, that follow the source through the expected rise, peak and decay of a flare, and gamma-ray observatories survey the region more broadly, in case very high energy emission increases. When these data are combined, they provide a time-resolved multi-wavelength portrait of each event. In flares believed to arise from disk impact by the secondary, the optical and ultraviolet bands often show a strong smooth component that can be approximated by thermal emission from hot gas, with a temperature of tens of thousands of degrees Celsius, while the polarization fraction drops as this relatively unpolarized thermal light dilutes the more strongly polarized synchrotron continuum from the jet. In some cases, the spectrum in these bands becomes bluer at the beginning of the flare, indicating that the characteristic temperature of the emitting gas is highest soon after the impact, and then gradually reddens as the gas cools, consistent with shock-heated material in the disk radiating away its energy. At the same time, the radio emission from the core may respond more slowly, sometimes brightening weeks or months after the optical peak, suggesting that disturbances triggered near the disk propagate outward along the jet and become visible at longer wavelengths only after travelling some distance and expanding. X-ray data show a more varied behaviour. In certain events, the X-ray flux increases roughly in step, with the optical and ultraviolet light pointing to a connection between the shock-heated disk gas and high-energy processes in the inner corona or jet base. In others, the X-ray response is weaker or delayed, which may indicate that the geometry of the emitting regions or the supply of seed photons for inverse Compton scattering has changed. Gamma-ray observations, while often limited by sensitivity, sometimes reveal modest enhancements during optical outbursts, further tying the highest energy electron populations to the episodes of disk disturbance. The combination of these patterns helps distinguish between competing models. In a purely jet-based scenario, large flares would be expected to show strong, highly polarized synchrotron emission across optical and near-infrared bands with correlated changes in radio X-ray and gamma-ray flux, driven by variations in the conditions within the jet. Thermal components with blackbody-like spectra would be harder to produce in this framework, and the polarization would not be expected to drop sharply during the brightest phases. In OJ287, however, several well-observed major flares show clear thermal signatures and polarization behavior, consistent with the substantial thermal contribution, supporting the idea that disk heating by the secondary plays a key role. At the same time, the presence of correlated or delayed high-energy emission demonstrates that the jet is not passive in these events, but responds to the changes in the inner environment so that the flare becomes a combined disk and jet phenomenon. Model testing proceeds in two main complementary ways. On long time scales, the sequence of major outbursts is compared with orbital calculations that include general relativistic precession and gravitational wave energy loss. For each assumed set of masses, spin values and initial orbital parameters, the model predicts the times at which the secondary crosses the disk, and thus the approximate times of thermal flares. Observers then check whether the recorded peaks in the optical light curve fall near those predicted times. The binary models for OJ287 have been able to match many decades of flare timings with impressive accuracy, often within a small fraction of a year, and predictions made in advance for future events have been borne out by subsequent observations, lending strong support to the underlying picture. Alternative models based on disk instabilities or jet precession alone generally find it more difficult to reproduce both the double structure of each major event and the long-term stability of the spacing between them. On shorter timescales, detailed simulations of disk impacts and jet responses are used to generate synthetic light curves and spectra that can be compared with real data from individual flares. Hydrodynamic and magnetohydrodynamic codes follow how gas behaves when a massive object plunges through the disk, producing maps of temperature, density, and velocity that can be turned into predicted emission in different bands. By adjusting parameters such as the disk density profile, the relative inclination of disk and orbit, and the viewing angle, theorists seek combinations that yield flare shapes and color evolution similar to what is observed. Although the complexity of the real system means that no single simulation captures every detail, broad agreements in rise time, decay time, and peak temperature provide further evidence that the basic impact picture is sound. Meanwhile, models of the jet incorporate shocks, turbulence, and changing magnetic field configurations to account for the non-thermal variability. They predict, for example, that a new shock launched near the base of the jet during or after a disk impact could accelerate particles and temporarily enhance synchrotron and inverse Compton emission, leading to a secondary high-energy flare that lags the thermal optical peak. Multi-wavelength data from OJ287 show events consistent with this pattern with gamma-ray or hard X-ray activity following strong optical outbursts, although the limited sensitivity and sampling of some instruments leave room for uncertainty. In addition to timing and spectral information, structural measurements contribute to model tests. Very long baseline interferometry images of the radio core and inner jet, taken before and after major flares, can reveal whether new components emerge or whether the jet direction appears to shift. In some blazars, changes in jet orientation over years have been linked to precession or to instabilities near the black hole. In OJ287, the connection between jet morphology and the binary orbit is still under investigation, but any systematic trends in component ejection times or position angles relative to the times of predicted disk crossings would offer another way to probe the interaction between orbit disk and jet. Polarization monitoring also plays a structural role, because smooth rotations of the polarization angle can signal the passage of a coherent magnetic structure or a change in the projected geometry of the emission region. By comparing these rotations with the phases of the orbit, observers can check whether particular orbital configurations tend to coincide with certain jet states. Finally, there is interest in connecting OJ287 to efforts to detect very low-frequency gravitational waves using pulsar timing arrays, which measure tiny variations in the arrival times of pulses from millisecond pulsars distributed across the sky. A binary as massive as the one inferred in OJ287 contributes only a small part of the overall background of gravitational waves expected from many such systems, and its individual signal may not yet be distinguishable. Nevertheless, the existence of a well-constrained, very massive binary at a known distance, and with an estimated orbital evolution, provides a valuable reference for models of the gravitational wave background, and for interpreting any future detection of individual supermassive binaries in this frequency range. In all of these ways, multi-wavelength campaigns turn OJ287 from a simple variable point of light into a richly characterized physical system where timing, spectra, polarization, and structure all act as tests of the binary model and of the physics of accretion and jets around some of the most massive black holes known. Each new flare becomes an experiment that either reinforces or challenges the current understanding, and the long, carefully monitored record of events allows models to be refined and extended rather than remaining speculative. The coherence between predictions and observations across many cycles, though not perfect in every detail, stands as one of the strongest reasons why OJ287 is now widely regarded as a key example of a supermassive black hole binary whose properties can be measured not only in terms of mass and luminosity, but also in terms of orbital dynamics, disk structure, and jet behavior, all constrained by light gathered from radio wavelengths to the highest energies that current instruments can detect. In the innermost regions of OJ287, where the gravitational pull of the primary black hole becomes overwhelming, and where the secondary approaches to within only a few tens of times the radius of the event horizon, the physics remains only partly mapped, even though the large-scale behavior of the system is now described with some confidence. The event horizon itself is the boundary within which no signal can escape a surface defined not by a material shell, but by the geometry of space and time around the black hole. For the primary in OJ287, with a mass of many billions of times the mass of the Sun, this horizon has a radius measured in light hours, large in absolute size but extremely small on the scale of the host galaxy. Just outside this surface, gas in the innermost accretion flow orbits at relativistic speeds, and magnetic fields thread the plasma and the space near the horizon. In this region, the distinction between the gravitational field of the black hole and the structure of the surrounding disk and jet becomes blurred, because the dynamics are governed by a combination of strong gravity, magnetohydrodynamics, and radiation processes. Current models of this zone rely heavily on numerical simulations that solve the equations of general relativistic magnetohydrodynamics, following how gas and fields evolve near a spinning black hole. These simulations show that turbulence driven by magnetic instabilities can transport angular momentum and heat the gas that magnetic flux can build up near the horizon and reconnect, and that jets can be launched when rotating field lines tap into the spin of the black hole and accelerate plasma outward. They also predict that the inner disk can become highly inhomogeneous with clumps, filaments, and time-dependent structures that vary on timescales comparable to the orbital period at the innermost stable circular orbit. However, translating these theoretical patterns into directly observable signatures is difficult, because the inner regions cannot be resolved spatially in OJ287. The system lies so far away that even the most powerful, very long baseline interferometry arrays, which can image the shadow of the central black hole in much nearer objects, see only a compact core at radio wavelengths without resolving horizon-scale structure. As a result, the properties of the inner flow and jet base must be inferred indirectly from spectra variability and polarization. One key uncertainty involves the spin of the primary black hole. The rate at which energy can be extracted from a spinning black hole to power a jet, and the location of the inner edge of the accretion disk both depend on how rapidly the hole rotates. In OJ287, the strength of the jet and the success of binary orbital models that include spin-related precession suggest that the primary may rotate rapidly, but the exact spin parameter is not yet tightly constrained. Estimates come from fitting the timing of disk-crossing flares with general relativistic orbits that include spin effects from modeling the overall spectral energy distribution and from analogies with other systems, but each method carries systematic uncertainties. A second uncertainty concerns the detailed structure of the inner accretion disk and corona. Observations indicate that a luminous disk must surround the primary, and that a hot, possibly magnetically supported corona above the disk contributes to X-ray emission. Yet the relative importance of different heating mechanisms, the vertical distribution of temperature and density, and the geometry of the corona remain only partly known. In many models, the corona is treated as a roughly spherical or slab-like region, but simulations suggest that it can be patchy, with regions of intense magnetic reconnection, producing localized flares. In OJ287, the strong non-thermal jet emission overlays much of the inner thermal spectrum, making it challenging to separate contributions and to use standard techniques such as X-ray reflection modeling to probe the inner disk. The binary nature of the system adds further complexity. The secondary black hole, when near pericenter, enters the region where relativistic effects are strongest. Its gravitational field perturbs the inner disk, and its path through the accretion flow changes with each cycle as the orbit precesses and shrinks. While orbital models treat the secondary as a point mass following a geodesic, in a curved space-time, the response of the gas and magnetic fields to its passage is far more intricate. Simulations of disk impacts capture some of this behavior on larger scales, but cannot yet fully resolve the region where the gas is both strongly magnetized and influenced by the spin of the primary. Thus, although the times of major flares can be matched to disk crossings, the microphysics that sets the exact spectrum polarization and detailed temporal structure of the emission remains incompletely specified. Another area of uncertainty lies in the coupling between the innermost disk and the jet base. The jet must be launched from within a few tens of gravitational radii of the primary, and its power direction and variability all depend on conditions in this region. In OJ287, long-term radio and optical monitoring suggests that the jet direction is broadly stable, but it is not yet clear whether small changes occur in response to the orbital motion of the binary or to changes in the inner disk structure. If the spin axis of the primary is slightly misaligned with the orbital angular momentum, then frame dragging effects can cause the inner disk and jet axis to precess, slowly, possibly imprinting a very long period modulation on the jet orientation. Detecting such precession would require precise long baseline measurements of jet position angles and polarization structures extending over many decades. At present, hints of structural evolution exist in some radio images, but they do not yet provide a definitive measure of slow precession. In the innermost region near the horizons, questions also remain about the composition of the jet. Theoretical models permit jets that are dominated either by electrons and positrons, or by a mixture of electrons and heavier ions, and the composition affects how efficiently energy is converted into radiation, and how the jet interacts with its surroundings. In OJ287, the available spectral and polarimetric data constrain the energy distribution of emitting particles, but do not yet uniquely determine the proportion of pairs to ions. Changes in composition, if they occur, could influence the relative strength of synchrotron and inverse Compton components during different states, but separating these effects from changes in magnetic field strength and particle acceleration efficiency is challenging. Looking ahead, several lines of observation offer ways to probe these inner regions more closely and to reduce the present uncertainties. Improved X-ray spectroscopy and X-ray polarimetry, provided by new and planned space missions, can help disentangle thermal reflection from the inner disk Comptonized emission from the corona and inverse Compton emission from the jet. Measurements of X-ray polarization angle and degree during both quiet and flaring states may reveal how the geometry of the emitting region changes and whether the corona is compact and centrally concentrated or more extended above the disk. In the optical and infrared, more sensitive interferometers that can approach micro-arc second resolutions may eventually provide images of the inner jet at smaller projected scales, revealing bends, knots, and possibly rotation signatures closer to the launch region than currently accessible. In the radio band, continued very long baseline monitoring can map the trajectories of superluminal components with increasing precision, allowing any long-term drift in jet direction to be measured and compared with expectations from binary-induced precession. Beyond electromagnetic observations, the evolution of OJ287 remains highly relevant to efforts to detect gravitational waves from supermassive black hole binaries. Pulsar timing arrays are beginning to report evidence for a background of low-frequency gravitational waves produced by many such systems. While OJ287 by itself may not yet be individually resolved, its well-constrained masses and orbital parameters make it a useful benchmark for population models that predict the strength and spectral shape of this background. Over time, as pulsar timing data accumulate and analysis methods improve, it may become possible to identify contributions from especially massive or nearby binaries. Space-based gravitational wave observatories planned for the coming decades aim to operate at frequencies intermediate between those accessible to pulsar timing arrays and ground-based detectors. Their most prominent targets will be merging supermassive binaries at smaller separations than currently inferred for OJ287, but the existence of systems like this one informs the expected rates and signal strengths. A future detection of any comparable binary would provide a direct independent measure of masses and orbital dynamics in the strong field regime complementing the indirect constraints already obtained from the light curve of OJ287. Even with these prospects, it is likely that some aspects of the region right above the horizons in OJ287 will remain beyond direct reach for a long time. The combination of great distance and small angular scales means that horizon-scale imaging comparable to what has been achieved for much nearer black holes will not be feasible with foreseeable instruments. Instead, the system will continue to be studied through the integrated signatures of its inner processes, the timing of flares tied to disk crossings, the shapes and colours of those flares as gas is heated and cools, the variability of the jet across the spectrum, and the slow drift of the orbit as energy is lost to gravitational waves and to interactions with the surrounding medium. Within these constraints, the innermost zones of OJ287 still offer a rare opportunity. Because the binary parameters are constrained by a century of data, and because the system is both massive and strongly relativistic, it serves as a test bed for theories of gravity accretion and jet formation under extreme conditions. Future observations will not transform the picture completely, but will sharpen it, turning broad inferences into tighter measurements and perhaps revealing subtle departures from current models. For now, the view into the regions near the horizons remains indirect yet remarkably informative, built from light that has travelled billions of years and encoded in its timing and spectrum the imprint of matter and fields moving in one of the strongest gravitational wells currently accessible to detailed study.